Welcome back. So we'll continue our discussion on this surface roughness and all this. So what we have talked about this flat terrain, non-flat terrain, how we kind of classify the this flat or non-flat. So quickly, what we talk about now on this, how this flow over these terrains and how to take care of that. Mm, In a nutshell, what this is going to do is that when flow passes over this terrain, obviously some kind of roughness effect would be there. Due to that, there would be some profile, and the profile can be estimated like either logarithmic or power law profile. And what you do that kind of get you an effect of this boundary layer, which would allow you to estimate the wind shear and the wind shear in turn the design part of it. So what we now talk about is that flow over terrain. So this could be flat, this could be non-flat. So I mean, whenever flow over terrains, for example, you have this is one. So there is a flow like that. So when the flow comes, passes over that, you have recirculation zone. So you have shear layer, you have outer layer, you have inner layer. So all these are possibilities. This is one of the things that when the flow passes over that, how it kind of. So this terrain structure could be different. So I mean, it could be, let's say, some kind of this kind of a structure where you have a flow field and the flow passing around that. So you might have different structure. So what you can have essentially flat terrains are quite that way simpler, but the non-flat terrain there could be different roughness effect. There could be small scale features. For example, if you have a surface like that, if you have a flow field and maybe this kind of roughness is there, so the velocity profile here is going to be some kind of a deflected. So this is small scale features. Okay, this can, then there could be large scale feature also, which could be possibly you can have, then different kind of shapes also possible. Okay, also possible. Now elevations are possible, which means sometimes flow over elevated terrain also kind of one can resemble that flow structure like an flow around the obstacle. So effectively what you think about, then you can have depression is one kind. Now these are all having flat terrain non-flat terrain with small structure. Now, if you have a non-flat terrain with large structure, then there could be non-flat with large-scale feature, large-scale feature. So you could have valley and canyons. Okay, you could have slow points. You could have prevailing winds in alignment. Okay, you can have prevailing winds in non-alignment also, alignment or non-alignment, gaps, passes, saddle, large basins. I mean, all these are kind of an characteristics of non-flat terrain or the large scale features. So what it what it does is that, so this kind of things are essentially you are having some kind of an obstacle over which your flow passes. So obviously when it passes through this obstacle, there could be some velocity deficit, momentum deficit. Effectively, your velocity profile gets affected. And once your velocity profile gets affected, that would impact the change in wind shear. And that is what is going to play key role in turbine power calculations and the design part of it. So now what we move on to look at is that wind data analysis. Okay. And also some kind of a resource estimation. What we are going to talk is the large quantity of wind data is when it is collected through measurement or instrumentations as whatever is possible. So then one can analyze that data in number of ways. So obviously one can do that in direct way. One can do that in statistical way. So you can analyze the data in different techniques. So what we would now discuss is that when we'll talking about this wind data analysis, we are going to look at the um, wind turbine energy production in general, a direct method of so direct method of data analysis, then some statistical analysis, and then statistically based wind turbine productivity estimates. So which are kind of again connected to the distribution, mean, variations, and all this. So we would look at these different ways to estimate those things. So the general aspect of wind turbine energy production is the available power from wind, let's say P half rho cube. Okay. So now one can see a graph which shows power output curve for a wind turbine. If this is my wind speed, then it goes to some kind of a, okay. So this is cut-in wind speed. Okay, this is power. This is rated power. This is cut-out wind speed. Okay. So this is how the typical curve, what it looks like. So this has three important portion. Was it the cut-in velocity, rated velocity at the rate, I mean rated power calculations at rated velocity, cut-out velocity. So when you talked about different methods, so that would also have some impact on this, how to analyze that. Especially when you try to use this direct data, which is averaged over a short time interval, and sometimes we can use method of beans, we can use velocity. Now let's look at first is that what are the direct methods for analysis. So the direct method for analysis, let's say, let's say you have a series of n wind speed observations, and each of them are ui, and this is average over time, which is delta t. Then the long-term average wind speed, long-term average wind speed, that is UR, that can be estimated as 1 by n summation of I to n ui. Similarly, one can find out the standard deviation, which is sigma of u, which, 1 by n minus 1 summation of I equals to n ui minus u bar square. If you arrange in slightly different way, then you can write this summation I equals to 1 to n ui square minus n ur square. So what you can also get average wind power density, that is P bar by A. So that is the average wind power available per unit area, which one can write half rho 1 by n. Okay. Similarly, we can have wind energy density, per unit area for a given time period of n delta t. E bar by a half of rho delta t 1 to n, which is p bar by a n delta t. Now we can have average wind machine power, which is that is 1 by n 1 to n pw ey. So this is the power output defined by a wind machine. So you can get this. Now the last one that one can estimate the energy from a wind machine, that is EW. That you write I equals to 1 to n PW delta T. Okay. These are different parameters that one can directly estimate from these things. Now, second way one can do that method of bins. Here, if your data is in this kind of a, let's say, this is your wind speed, and you have some data like that, so these are, you can say that number of occurrences. Okay, so you have kind of a, for at every wind speed, there is a these are at every wind speed you get some kind of a data which are in forms of a, so it's an this particular method also provides a way to summarize wind data and to determine expected time productivity. So obviously, what one has to do, the data has to be separated into the wind speed intervals or bins in which they occur. It is most convenient to use the same size bins. Let's say if you have, let's say NB is the number of bins and bin width is WJ, where the midpoint is MJ, and with number of FJ is number of occurrences in each bin or frequency, so that you have N is summation J equals to 1 FJ. So then one can find out Similarly, this average wind speed would be summation g equals to 1 to nb mj fj. Similarly, one can find the variation, which is 1 by n minus 1 j equals to 1 to nb mj square fj minus, which is 1 by n minus 1 j equals to 1 to nb mj square fj minus n. Similarly, you get p bar by a, which is half rho 1 by n nb fj. Then you have pw bar, which is pw mj fj j equals to 1 to nb. So you can have data, and then from there actually you can estimate the all these things from there. So this is how you can use this method of beans. And also what you can estimate the velocity curve, you can estimate the power duration curve. So all this you would be able to estimate using this kind of methods. So now what we can also the statistical analysis. Statistical method or analysis. So the statistical analysis can be used to determine the wind energy potential of a given site and to estimate the energy output from wind turbine installed in at given site. So then for statistical analysis, the probability distribution is the term that describes the likelihood that certain values of random variable, which is in this particular case is wind speed, will occur. Probability distributions are typically characterized by the probability density function or cumulative. So you need probability density function or cumulative density function. So what is probability density function? So if you talk about probability density function, which is PDF or P of U for wind speed, probability density function. So it's that you can say that P of U, the probability of occurrence of U between these two value is the probability distribution function of U. That is what it is. So it's a probability of occurring wind speed between UA and UB. So this is how one can define the distribution function. So that means we have specified a particular wind speed. Probability of occurring that is the one that um, so the important property of probability density function is that the total area under probability density curve is 0 to 1 PU du1. So once the probability density function PU is known, then you can find the mean speed, which is U bar, using the U PU du. Similarly, you can find standard deviation. So sigma U, which is 0 to infinity, where PU du. So mean available wind power density, that is P bar by A, that is half rho 0 to infinity. So half rho U bar cube, or one can say U cube bar is expected value. So once the probability density function is known, then you can estimate all this value. And the distribution function CDF represents the time fraction or probability that wind speed is smaller than or equal to a given wind speed U. Fu, which is cumulative distribution function, is the probability of U prime less than equals to U. Here U prime is a dummy variable. So what you can show that f of u is 0 to u, u prime du prime. Also, you can have probability density function of u is the derivative of f of u. So the derivative of cumulative distribution function is give you the probability density function. So that means the velocity duration curve is closely related to the cumulative distribution function. Commonly used probability density functions, okay, which we have already that like Gaussian distribution, you have Weibull distribution. So you have a Rayleigh distribution. These are the standard distribution function that you already we have discussed. What we can do, we are reiterating these things again because these are very, very key aspect in context of wind power estimation, because since you don't have the continuous similar kind of wind, so there is a distribution of the wind and all these things. So we'll quickly again recap those distribution function. and then like to calculate some of these parameters in next session. Okay, thank you.